Welcome to the Deep Dive, the place where we cut through the noise and synthesize the complex, often hidden elements that define modern technology.
Hello.
If you were preparing for a meeting, leading an engineering team, or, overseeing the integration of AI into high-stakes operations, you already know the difference between a cool prototype and a truly trustworthy system.
Mm-hmm.
It's a huge gap. It is. And today we are diving into the engineering blueprint of how to bridge that exact gap. We're moving way beyond the simple LLM chat window and focusing entirely on the architecture of reliable production-grade AI systems.
Exactly. And for those of you who are building, deploying, or overseeing these systems, especially in environments like, say, financial services, BFSI, where compliance and predictability are just non-negotiable, the journey from a proof of concept to deployment involves a whole stack of engineering challenges.
Challenges that are completely new.
Completely unique to generative AI, yeah.
Yeah. Our sources today are a dense, synthesized stack covering the full spectrum of modern AI engineering, the foundational DNA of large language models, the architecture of specialized AI agents, the mechanics of retrieval-augmented generation HE, and the crucial, rigorous MLOps practices you need for production reliability and security.
So our mission today really is to transform this very complex body of knowledge into actionable insight for you. We're going to unpack the essential, often hidden components.
The stuff that really makes it work.
Yeah, the stuff that makes it work. From, meticulous data quality, filtering techniques that define performance, to multi-agent coordination strategies, and the critical statistical drift detection metrics that keep a system trustworthy for years.
Okay, let's unpack this right away with what feels like the core philosophical challenge that just permeates all the source material. The moment you introduce an LLM into a workflow, you're dealing with a model that is inherently probabilistic.
Right.
It doesn't give deterministic answers, ever.
And that is the central tension of modern AI engineering. You want great performance. You want the model to be insightful, accurate, capable of complex problem solving.
But you also need it to be reliable.
You simultaneously require high reliability, predictability, and bulletproof security. So building reliable systems on top of these fundamentally probabilistic foundation models, or FMs, it demands a level of rigorous discipline across the entire stack that, frankly, traditional software engineering just never required.
So if you miss a step somewhere,
If you miss a step in data hygiene or observability or governance, the probabilistic nature of the model is what will dramatically surface those errors, and often in completely unpredictable ways.
So let's start at the very beginning with the foundational DNA. How these massive language models are actually, taught. The engine that drives modern general intelligence and AI is a mechanism called self-supervised learning.
This was a revolutionary conceptual breakthrough in machine learning. It basically solved the massive bottleneck of human labeling. Instead of needing millions of explicitly labeled examples, this is a credit application, this is a spam email, the system learns to understand data by generating its own labels directly from the input data itself.
So it's essentially teaching itself the structure and meaning of language by, playing internal statistical games with the text it consumes?
Precisely. For LLMs and the transformer architecture, this usually means masked language modeling, or more commonly now, just predicting the next word in a sentence.
Okay.
You feed the model truly vast amounts of unlabeled text, a massive corpus of the web, and it just learns the statistical patterns necessary to generate coherent human-like text. This process is crucial not just for text generation, but for building that broad foundation of general knowledge that makes the model so adaptable.
Right, especially where labeled data for specific niche tasks is scarce or just impossibly expensive to get.
Exactly.
And this foundational training leads directly into what the sources are calling the data quality paradox. You read constant headlines about the sheer volume, these data sets measured in trillions of tokens.
The volume is staggering, yes.
Yeah.
I mean, sources mention benchmark datasets like FineWeb, which has something like 15 trillion tokens derived from common crawl data.
Wow.
But the consensus among leading experts has shifted entirely. Volume alone, it delivers sharply diminishing returns. If you want better performance and faster training, you achieve superior sample efficiency by prioritizing quality over sheer quantity.
So better data means you need less of it.
A lot less. High-quality, curated data provides a dramatically better signal-to-noise ratio, which means you need less of it to teach the model the same task, and that can save billions of dollars in training compute.
Okay, so if volume is out and quality is in, how does an engineering team actually operationalize quality across a petabyte scale corpus. This is where the specific, rigorous preprocessing techniques come in, right?
Absolutely. The data preprocessing pipeline is the invisible foundation of model performance. And there are three critical details in the sources we should highlight. First, deduplication. You have to remove massive sequence-level duplicates. We're talking about things like boilerplate legal text, terms of service, or, widely repeated documentation sections that can be accidentally repeated thousands or even millions of times across a web-crawled dataset.
I get the computational benefit there. I mean, why train on the same 5 paragraphs of legalese 1,000 times? But I see in the sources that this is essential for unbiased evaluation and trustworthiness. Can you expand on that?
Yeah, it fundamentally corrupts your ability to measure generalization. In a robust MLOps process, you set aside a pristine validation set to measure true performance.
Right, the holdout set.
Exactly. If your training data and your test data overlap, even by these common sequences, the model hasn't learned to generalize. It has simply memorized the test answer.
I see.
This results in an artificially inflated performance score, creating a dangerous sense of false confidence in a system that hasn't proven its actual capabilities.
So what's the tool for that?
Well, deduplication methods, often using algorithms like minhash, which generate these locality-sensitive hashes to find near duplicates efficiently, are absolutely essential here. They break that structural overlap and ensure an honest evaluation.
So the first critical detail is realizing that data hygiene is synonymous with honest model evaluation. If minhash prevents this structural overlap, what's the next step in actively judging the semantic quality of the remaining data?
So now we move into the proactive operationalization of quality. One key method uses a concept called perplexity.
Perplexity.
Perplexity measures how well a language model predicts a given text. Lower is better. The process involves training a smaller reference language model exclusively on known high-quality sources, like a curated scientific index or Wikipedia.
So you're using a small, clean model to judge the data for the big one?
Exactly. Then you calculate the perplexity of every document in your potential training set over that reference model.
That's fascinating. It's like you're using a pristine, well-behaved model to be the quality gatekeeper for the massive model you're trying to build.
Precisely. Documents with high perplexity, meaning the quality model struggles significantly to understand or predict them, are filtered out as statistical noise or low-quality content.
Sounds expensive.
It is computationally expensive, especially across 15 trillion tokens, but the resulting sample efficiency pays huge dividends. And a parallel, complementary approach uses token distribution KL divergence.
And KL divergence is a statistical measure of how far one probability distribution is from another, right?
Correct. In this context, it flags documents whose token distribution deviates statistically too far from a known, clean reference distribution. This is highly effective for catching outright spam, automatically generated gibberish, or text in a completely different domain than you intended. It helps you surgically remove documents that would otherwise pollute the training process.
And the third critical detail touches directly on safety and privacy, which is absolutely paramount for our listeners in BFSI.
That's PII remediation, or the removal of personally identifiable information. And it is sobering to note that most of the early landmark pre-training datasets underwent little to no PII remediation.
Holy.
Yeah. This creates a severe risk of data leakage or memorization, where the LLM can reproduce parts of its training data, including private customer details, if you prompt it in just the right way.
That's a huge liability.
Massive. Projects like the Big Science effort had to develop specific, detailed pipelines for PII detection and remediation just to address this vulnerability. For any application handling sensitive data, this step is non-negotiable and often requires sophisticated techniques that go way beyond simple regex matching, utilizing other models trained specifically for named entity recognition of private data.
So once the data is pure, we move to the architecture of the model itself. We hear about transformer models all the time, but what are the primary structural choices engineers are making when they select a backbone?
You basically have three main transformer backbones, and they're defined by what their attention mechanisms focus on. Encoder-only architectures, like the original BERT, are ideal for understanding and classification tasks.
Okay, so things like sentiment analysis.
Exactly, where you need to analyze the entire input text simultaneously, like determining the sentiment of a customer review or classifying a fraud ticket. They process the whole sequence at once.
And the ones that actually generate text, the ones we're most familiar with now.
Those are the decoder-only architectures. That's what most modern large LLMs use. Think GPT variants or Llama. They focus on generation, predicting the next token in a sequence, and they only attend to tokens that came before. They were state-of-the-art for creative text, dialogue, and code generation.
And the third type.
Finally, you have the encoder-decoder architecture, which was the original transformer design. It processes the input with the encoder and generates the output with the decoder, maintaining a standardized interface for multiple tasks. You see this in models like T5. They excel at tasks like machine translation or summarization, where the input and output structures are different.
I think we often forget how fundamental the engineering of language breakdown is. It's not just words, it's tokens.
And tokenization is such a critical engineering detail. Text is broken down using subword tokenization. The most common algorithms are byte pair encoding, or BPE, and word piece.
How do those work?
BPE works by repeatedly merging the most frequent consecutive pairs of characters or tokens until you hit a desired vocabulary size. Word piece is similar, but it uses a maximum likelihood score to decide which pairs to merge, prioritizing merges that maximize the probability of the resulting token appearing in the whole corpus.
So when we see a technical term or a large number like 9342 being split into multiple tokens, 93 and 42, that's BPE, or word piece, optimizing the vocabulary size, right? Because they're prioritizing common sequences.
Exactly, it's a trade-off. It's just impractical to give every single technical jargon term, every URL, or every permutation of numbers its own token. These subword algorithms ensure the vocabulary remains manageable, maybe 50,000 unique tokens, while still efficiently representing both common words and complex rare subwords or sequences. This is a foundational step that heavily influences both model size and training efficiency.
And for any sequence data, order matters. How is that word order efficiently encoded for the transformer architecture, which otherwise has no inherent concept of position?
That's the function of positional encoding. Since the self-attention mechanism in transformers treats all tokens simultaneously regardless of their position, the model needs an explicit way to know where each token sits. While older methods use static functions, advanced techniques like rotary position embedding, ROPE, and attention with linear biases, LIBARI, are now pretty much standard in state-of-the-art models.
And how do they improve on the older static methods? What's the advantage?
Well, ROPE is particularly clever because it applies position encoding implicitly during the attention calculation using a rotation matrix. This preserves the relative positional information when calculating attention scores. Critically, these advanced methods are key to enabling extrapolation.
Meaning?
They allow the model to effectively handle much longer sequences during inference modeling, longer contexts, than the absolute sequence length they were initially trained on. And that's a massive win for production use cases involving long documents.
So when an engineering leader is tasked with selecting an LLM for a production task in finance, what are the 3 criteria they must focus on beyond just the standard MMLU score?
Well, performance benchmarks are only the starting point. They have to consider the operational costs, both inference and fine-tuning compute expenditures, and critically, the user experience metrics. Specifically, they need to benchmark time per output token, or TPOT.
TPOT, that's a direct measure of perceived latency for the end user.
Yes, if your model takes 5 seconds to generate a response, the user experience suffers severely, especially in synchronous applications, regardless of how accurate the output is. Fast throughput is crucial for perceived reliability.
And this focus on efficiency brings us to the promise of smaller models, which has become a major trend over the last year.
It has.
It seems counterintuitive, right? We're talking about models with fewer than 8 billion parameters when the big news is always about models with over 100 billion.
Small models are a pragmatic necessity. They are resource efficient, often capable of being run entirely on local private infrastructure without the cost and latency of cloud API calls. And while they may not have the general knowledge breadth of the largest models, when you finally tune them to a specific enterprise task or domain like processing BFSI compliance documents, they are highly effective, they minimize latency, and they drastically reduce compute costs.
So for a specific scoped enterprise application, the small model is actually a huge advantage.
It's a massive advantage over larger, slower counterparts. It's the classic engineering trade-off of breadth versus depth and speed.
We've engineered the language engine. Now we shift to giving it purpose and the ability to act. The jump from a powerful LLM to an AI agent is the jump from passive answering to dynamic, autonomous, multi-step action.
That is the critical distinction. We define an AI agent as a system powered by a foundation model that's capable of dynamic, multi-step planning, continuous learning from feedback, and autonomous decision-making within, well-scoped areas. They don't just react to a prompt. They analyze, they plan a course of action, execute that plan using tools, and then they reflect on the outcome.
And this capability is what differentiates agents fundamentally from the rigid, rules-based workflows that preceded them in traditional enterprise automation.
Exactly. A traditional rule-based system or a basic state-machine workflow,
Yeah.
it just shatters when it's faced with unstructured, novel, or highly variable inputs.
Right.
Imagine a customer support queue. A rigid system can handle, I need to cancel my order, or what is my current balance? But what about an email that blends product failure, billing confusion, and a threat to switch providers?
Yeah, that spans technical, financial, and emotional domains all at once.
An agent handles this by parsing the free-form text, extracting the multiple intents, dynamically consulting a knowledge base for technical specs and a CRM for billing history, deciding on the optimal next steps, like drafting a response and initiating a ticket escalation, all without being pre-programmed for every possible conversational branch.
So that dynamic adaptability to unstructured data is the core advantage.
It is, particularly when you're dealing with the complexity inherent in customer-facing BFSI interactions.
So for an agent to actually do anything external to its own internal reasoning, it needs capabilities, the hands and feet we read about in the source material. These are the tools.
Tools are the fundamental capabilities that enable agents to perform specific functional actions or solve problems that the LLM just can't handle internally. They are discrete, tailored functional building blocks.
Like what?
These can range from internal tools like simple calculation functions or structured data retrieval from local databases to critical API-based tools that connect with external real-time services. A tool to, say, update customer address, get stock price, or initiate transfer.
Okay, since tools are the agent's point of interaction with the outside world, security here has to be paramount. This is where these systems move from being merely helpful to potentially dangerous.
The security and safety discipline around tool use is perhaps the single most important component of agent engineering. A core security principle is the principle of least power.
Meaning?
You only give the model the tools and the specific capabilities within those tools that it strictly requires to achieve its defined purpose, nothing more.
And what specific safeguards are necessary for a production deployment?
You need multi-layered safeguards. This includes restricting capabilities within the API wrapper, rigorously sanitizing the model's inputs to the tool to prevent malicious arguments, and enforcing the least privilege doctrine on the back end. The agent should only access the data it is authorized to touch.
Okay.
And critically, we see a universal recommendation in the sources. Log every single tool invocation.
Why is that comprehensive logging so vital?
It's essential for compliance, for observability, and for forensic analysis. In a regulated environment, if something goes wrong, an unauthorized data query, an unusual deletion, or an anomalous behavior during a financial transaction, you need a full, immutable trace of what the agent invoked, with what parameters, and the resulting system output. This discipline transforms random, probabilistic failures into manageable, auditable, and predictable behavior.
Moving from the technical layer to the user experience, UX is critical for adoption and building trust. How should users effectively interact with these dynamic systems across different mediums?
UX design is just foundational for trustworthiness. Agents have to support seamless interaction across multiple modalities. Text is the default. It excels in precision, it allows for traceability, you have a record of the conversation, and it supports asynchronous communication like via Slack or Teams.
But the shift is definitely toward more interactive and graphical interfaces.
They are. Graphical interfaces, GUIs, are excellent for structured interactions, data visualization, and rapid status updates. Think of tools like GitHub Copilot or advanced financial modeling agents that generate dashboards. These interfaces reduce the ambiguity that's inherent in chat and offer users a tangible sense of control and status updates on complex, long-running processes.
And the sources suggest the future of work might shift heavily away from documents toward these kinds of interfaces.
That's right, toward these interactive, agent-driven interfaces that are purpose-built for high-velocity decision-making.
And then there's the growing importance of speech and voice interactions.
Voice offers unparalleled convenience for hands-free tasks and quick, high-level queries. A trader asking for a summary of market volatility while driving. However, it's fundamentally poor for consuming dense information or complex decision-making that requires side-by-side review or deep scrutiny.
Which means the agent needs the intelligence to know when and how to switch the communication method.
That's modality fluidity. The agent has to adapt its communication style, delivering concise spoken summaries, but providing detailed, citation-rich textual outputs for review later. More importantly, it must maintain state and context persistence across those transitions.
So it can't forget what you were talking about when you switch from your phone to your laptop.
Exactly. Information, task progress, and user preferences should never be lost when a user moves from a voice query to a follow-up GUI interaction or a detailed text report. This requires highly sophisticated session and state management architectures. And if context is forgotten, the agent must not proceed with assumptions. Instead, it has to gracefully recover by pausing and asking clarifying, unambiguous questions.
That concept of state management and risk leads directly into the ultimate design choice. How autonomous should the agent be in any given scenario?
This is defined by the autonomy slider pattern. This is an architectural design that allows systems to fluidly shift execution modes based on the current query complexity, the inherent risk profile of the action, or regulatory requirements.
Okay, let's define the three positions on that slider, starting with minimum autonomy.
We begin with manual autonomy. Here, the human is the sole executor of the task, but the agent acts as a powerful co-pilot, providing real-time information, suggestions, or analysis. For example, synthesizing data from multiple databases during a high-stakes client call.
And the next step up.
Next, we have assisted autonomy, also known as human in the loop, or HITL. This is really common in customer service agents. The agent drafts a report or suggests a potentially impactful action, like an email reply or a transaction, but the human reviews and explicitly approves the action before execution. This accelerates the workflow while maintaining crucial human judgment and legal oversight.
And finally, the goal for many high-volume, routine enterprise tasks, full autonomy.
Autonomous mode. The agent handles routine, lower-risk queries or high-volume, structured tasks like order tracking, basic password resets, or routine compliance checks without any human intervention. It only escalates complex, novel, or highly sensitive issues to a human governor.
So the key is in the design.
It's all conscious design. An underpowered agent requires too much manual input, and that frustrates users. An overbearing agent acts without consent in sensitive contexts, and that erodes trust. The slider has to be tuned to the specific risk tolerance of the organization.
And for all these modes, managing memory context retention is essential for continuity.
Yes. Memory is partitioned. Agents use short-term session memory for the immediate ongoing interactions details. However, complex systems, especially those dealing with tasks that span days or involve multiple parallel agentic threads, they require persistent state management.
So saving the game, basically.
Exactly. It means storing the current task progress, the decisions made so far, and any collected data in a durable store, allowing users or other agents to resume a long-running task days or even weeks later. And robust error handling and state management is key to preventing the agent from getting stuck in an infinite loop or making dangerous, unfounded assumptions.
Moving to the architecture, designed for performance and scale, we have to address the single biggest technical trust inhibitor: the LLM's tendency to hallucinate, to confidently generate plausible but fabricated information. The solution, the architectural cornerstone, is retrieval augmented generation, or RAG.
RAG is absolutely central to building reliable, high-stakes systems. Its core purpose is to augment foundation models with external, up-to-date, ground truth data stores. This dramatically reduces the risk of hallucination, and, equally importantly, it enables accurate citation, connecting the generated output directly back to the verifiable source document.
This often leads to the critical engineering decision. Should I fine-tune my model, or should I implement RAG? The sources suggest they address fundamentally different problems.
They do, and often they're combined. RAG is universally superior for imparting new or rapidly updated facts or external knowledge like recent policy changes, real-time market data, or a new quarterly report that the model wasn't trained on.
Okay, so it's foreknowledge.
It's foreknowledge. Fine-tuning, conversely, is better for teaching the model a specific input-output mapping, improving its tone, adopting a domain-specific style like highly formal, legally precise BFSI language, or modifying a complex behavioral pattern. If you need the agent to follow a specific regulatory template, you fine-tune. If you need it to incorporate today's stock price, you use RAG.
To make R work, the system must efficiently find the relevant information in those massive external databases. This starts with the source documents. Why can't engineers simply chunk documents by paragraph or sentence?
Because simple splitting fails to maintain semantic coherence. Paragraphs are grammatical units, not necessarily units of meaning.
I see.
We need chunks that represent a semantically coherent unit of knowledge. The reason is technical. Embedding models, which convert text into vector representations for semantic search, have limited context windows. If a chunk is too long or contains irrelevant context, the resulting embedding vector will be diluted, and the effectiveness of the similarity matching just decreases dramatically. Effective RAG demands semantically relevant, concise chunks.
And speaking of embeddings, how do we make that retrieval process faster and cheaper without sacrificing the accuracy that ARG depends on? Retrieval is often the highest cost and latency component.
This is where advanced techniques like Matryoshka embeddings offer a fascinating optimization. Traditional embeddings are large, maybe 24 or 768 dimensions, and they're computationally expensive to store and search. Matryoshka embeddings are designed such that they preserve nearly all of the original performance sources, suggest 98.37%, even when the embedding vector is significantly truncated down to a much smaller size, say 256 dimensions.
So you can use the smaller truncated vector for the majority of fast, cheap searches, knowing that the quality correlation is maintained.
Exactly. The inner product similarity calculation, which is the heart of vector search, remains highly accurate despite the truncation. This makes the retrieval stage far more cost-efficient and drastically faster, which is essential for scaling RG systems in high-throughput enterprise environments, where a millisecond of latency costs real money.
Standard vector retrieval works well for many fact-seeking queries, but for complex interconnected data, especially the kind of dense cross-referenced policy documents common in BFSI, that strategy starts to break down.
That limitation cues the use of advanced knowledge structures, specifically GraphRag. GraphRag shifts the paradigm from simple vector searching over unstructured text chunks to querying a highly structured knowledge graph.
A knowledge graph.
Yeah, this graph is built by extracting semantic, triple subject predicate object expressions from the documents. These triples define explicit relationships, and they're often stored in graph databases like Neo4j.
So instead of asking which document mentions the policy on X, you're asking what is the relationship between policy X, the regulatory requirement Y, and the penalty Z?
Precisely. This graph structure enables far more sophisticated reasoning capabilities, including multi-hop retrieval, where the agent connects multiple distinct pieces of information across the graph to synthesize a non-obvious answer. If standard vector retrieval hits limitations when you need to reason over complex policies or technical dependencies, GraphRag, despite being significantly more complex to implement, often yields demonstrably better and more reliable results in high-complexity environments.
That complexity is a key engineering trade-off. Building that ETL pipeline to extract those semantic triples and maintain the graph seems like a massive engineering burden compared to simple chunking. Is the payoff worth the data pipeline debt?
For generalized chatbots, probably not. But for specialized agents that handle regulatory compliance, complex financial modeling, or intricate supply chain logistics, the payoff is essential. The ability to perform logical inference and consistently surface those critical interconnected relationships mitigates regulatory risk and increases decision quality far beyond what a simple vector search can provide.
So it shifts the system from informational retrieval to true knowledge reasoning.
That's it.
Now that we know how to ground a single agent, let's talk about scaling across a whole organization, coordinating multiple specialized agents. What are the advantages of multi-agent systems, or MAS?
Multi-agent systems are necessary for tackling complexity that exceeds the capability of a single model. They offer three major advantages: collaboration and specialization, where you assign dedicated roles. One agent collects data, another analyzes risk, and a third interacts with the user. Parallelism, allowing simultaneous execution of subtasks.
Like checking inventory and delivery status at the same time.
Right, or payment authorization.
Right.
And crucial adaptability, where roles can be reallocated dynamically in response to new information or changing conditions, which provides better resilience.
To manage these specialized agents, you need architecture. How do we structure their coordination to prevent chaotic or conflicting actions?
The sources detail three primary coordination architectures. Centralized coordination uses a supervisor agent to direct and monitor all work and arbitrate conflicts. This is effective in structured, highly regulated settings where control is paramount.
Okay.
Then you have decentralized or democratic coordination, where agents communicate directly and bid for tasks based on their capabilities. This is highly flexible, but inherently complex, prone to communication overhead and potential deadlock.
And the third option tries to combine control and flexibility.
That is the hierarchical coordination model. It combines centralized control with distributed responsibility. Higher-level agents oversee and direct the overall goal, but subordinate agents retain a defined degree of autonomy within their assigned scope. This provides the best scalability and fault tolerance because coordination responsibilities are distributed across multiple levels, preventing a single supervisor from becoming a bottleneck.
This inherent complexity means agents need a standardized way to communicate, not just with each other, but with external systems, regardless of the underlying LLM.
This is the crucial requirement for agent-to-agent, A2A communication. The Model Context Protocol, or MCP, which was developed initially by Anthropic, is being envisioned as the USB-C port for AI. It's an open standard, providing a uniform, model-agnostic way for LLMs to connect to external systems like HTTP servers or subprocesses.
So the MCP standardizes the critical interaction components, the tool definitions, the data schemas, the error handling responses. So agents built on different foundational models can interact seamlessly.
Precisely. It abstracts away the complexity of building brittle, bespoke adapters for every data source or every internal API. Adopting a standardized communication protocol is a critical step in building interoperable, scalable, multi-agent systems that can truly be integrated into existing enterprise IT infrastructure.
And finally, what tools are helping developers structure these increasingly complex nonlinear agent workflows?
They're relying on powerful orchestration frameworks. Tools like LangGraph structure the relationship between agents and their tools as a directed graph of asynchronous function calls. Unlike simple linear chains, this graph allows for complex, nonlinear workflows with dynamic branching and merging tool executions.
So an agent can decide, I need to analyze the user query and simultaneously look up two different databases. If one lookup fails, I branch to a recovery step, then merge the successful results later for the final synthesis.
Exactly. This capability for complex, nonlinear planning is what enables the sophisticated reasoning and fault tolerance we expect from truly autonomous production-grade agents.
We've engineered the model and architected the system. Now we have to deploy it safely and reliably. This requires robust MLOps, the necessary extension of DevOps tailored for the unique dynamics of AI systems.
MLOps formalizes the full AI system lifecycle: development, build, test, deploy, operate, and monitor. For generative AI, the deployment process must explicitly account for the dynamic, probabilistic nature of the model itself.
Right, because traditional software is static once you deploy it.
It is. A model, even a static one, reacts dynamically to its inputs.
One clear warning from the sources, and this is vital for regulated industries, is the risk of dynamic updates.
Caution is essential here. You have to rigorously caution against dynamically updating models in production using live user data without full control. While it sounds appealing to keep the model immediately current, it completely bypasses established, rigorous deployment pipelines, automated testing, security checks, and audit trails.
So when an incident occurs, you have no clear record of the system state.
Exactly, which violates compliance requirements. You need a controlled, phased process for change introduction.
So if we can't update dynamically with live user data, how do we introduce and test new versions safely? We rely on phased rollouts.
We have three primary methods for testing in production. Canary deployment involves gradually exposing a new agent version, A prime, to only a tiny subset of live user traffic, maybe 1% or 5%. If key metrics, latency, error rates, token costs remain stable and acceptable, you slowly increase exposure.
And then there's shadow deployment.
Yes, and this is indispensable for high-stakes agents, like those making financial decisions.
The rehearsing a play backstage analogy.
Precisely. You run the new agent version in parallel with the live system on identical production inputs, but only the live system's output ever reaches the user. The new agent's outputs are logged and scrutinized, checking for differences or errors against the live system's results, shielding the user from any potential mishaps while gaining real-world performance data.
And the third?
Finally, A/B testing splits users 50-50 between two fully live variants, A and B, to measure performance differences directly in live interaction. You use statistical significance tests to determine which variant performs better against a defined goal, like reducing call center escalation rates.
Once deployed, we need deep insight into the black box. This is where we see the shift from simple monitorability to true observability.
Monitorability is tracking simple, predefined metrics like latency or CPU usage. Observability is the far more sophisticated ability to understand the internal state of the system. Specifically, the complex, non-deterministic decisions happening inside the LLM and the agent workflow. This requires LLM native monitoring.
Meaning we need to capture semantic and financial insights beyond just standard infrastructure health.
Exactly. We need metrics like hallucination rates, tool efficacy. Did the agent correctly decide to call the tool, and was the result useful? And distribution shifts in user inputs. To achieve this level of telemetry, engineers rely on highly integrated monitoring stacks.
Like what?
OTel, Open Telemetry, provides the foundational framework for structured, interoperable telemetry. It instruments the flow by placing trace hooks on the nodes within a complex orchestration workflow, like a line graph run.
So OTel gives us the trace flow, and then a tool like LangFuse provides the agent-specific LLM native metrics within those traces.
That's the architecture. LangFuse is tailored specifically for agents, offering crucial metrics like token cost tracking, which is essential for budget control and optimization, hallucination auto-evaluation, and session replay. You can log a full agent session, including all internal thoughts and tool calls, allowing for rigorous forensic debugging and regression testing later.
And you need to visualize this all somewhere.
And that's where robust tooling like Grafana is essential for dashboarding all these key metrics: P95 latency, usage costs, tool fallback frequency, and token consumption per agent per hour. It gives the governors a high-level view of system health and performance.
That kind of deep visibility is crucial for detecting the inevitable decay of the system over time. Let's talk about model drift. This is where the probabilistic nature of the model meets the unpredictable reality of the market.
Model drift is the slow, insidious decline in predictive accuracy due to fundamental changes in real-world data patterns. If your fraud detection agent was trained on 2023 transaction types and 2025 sees a massive, unexpected shift to new peer-to-peer payment fraud tactics, the model will quietly start failing.
And we can't wait for an accuracy score because the ground truth, whether a transaction was truly fraudulent, might take days or weeks to become available. We need statistical tools to detect shifts immediately, based purely on the input data distribution.
Correct. We need leading indicators. The first key statistical tool is Kullback-Leibler, KL divergence. This is used to measure rapid shifts in the statistical properties of the incoming data itself. Specifically, engineers track shifts in the token frequency vectors between historical data, the baseline the model was trained on, and the current incoming data.
So if user inputs suddenly start including a massive surge of new technical jargon or financial instrument names, things that weren't frequent in the training set, the KL divergence spikes, signaling concept drift even before the outcome is known.
Exactly. It measures the severity of the change in the incoming semantic landscape. The second critical tool focuses on detecting shifts in categorical variables, like the tools the agent is choosing to use.
That's the Population Stability Index, or PSI.
PSI is vital for assessing structural shifts in behavior. For instance, in a BFSI customer service agent, you might track the usage of specific tool categories: loan modification, new account opening, and fee dispute. If the PSI shows a sudden persistent spike in the loan modification category, even if the overall input volume is steady, it signals a major shift in customer financial hardship patterns.
And what are the intervention thresholds for PSI? When do you act?
A PSI below 0.1 signals stability. Between 0.1 and 0.25 suggests minor change that requires observation. Crucially, a PSI score greater than 0.25 signals major drift requiring immediate intervention, often necessitating the retraining of the underlying agent components or updating the ROE knowledge base. This statistical severity score is what guides the engineering team's response strategy.
So once drift is detected and quantified, how do teams respond? You mentioned the response must be proportional.
It has to be. Transient changes, a single-day spike might only require tuning the alert thresholds or manually reviewing a sample of the input data. But persistent systemic shifts, where that PSI greater than 0.25 threshold persists over, say, 48 hours, that requires significant intervention.
Like retraining.
It could mean emergency retraining workflows, integrating new data sources, or adapting to new versioned APIs. Strong feedback loops, which log and export the degraded traces detected by the monitoring stack, are essential for making that high-stakes decision. Is this a temporary anomaly or a systemic failure?
The ultimate aspiration for an agentic system is continuous learning and self-improvement without a human constantly performing manual updates. This leads us to non-parametric learning.
Non-parametric learning is the holy grail. Improving the agent's performance and behavior without having to update the massive multi-billion parameter model weights. The most adaptive way to do this is through dynamic few-shot selection. Instead of embedding static, predefined examples in the prompt, the agent retrieves the most relevant past examples or successful interactions from a vector database at runtime to include in the current prompt context.
This makes the agent instantaneously adaptive to the specific query, pulling in high-performing examples that match the current task.
It creates a highly resilient, low-latency learning loop, We also see agents teaching themselves by reflecting on their own past decision-making.
Right, the reflection paradigm.
That's the reflection paradigm, expanded by systems like Expel. The agent loop includes an internal self-verification and correction step, where it judges its own generated output before presenting it. Expel builds on this by adding cross-task learning. The agent maintains a persistent list of upvoted and downvoted insights extracted from successful or failed past experiences, allowing successful reasoning strategies to transfer seamlessly to new, related tasks.
And finally, let's discuss the automation of the most tedious task in early AI engineering, manual prompt engineering.
This is where frameworks like DSPy declarative self-improving language programs offer a paradigm shift. Instead of relying on manual trial and error prompt engineering, where you spend days just tweaking the exact wording, DSPy treats the LM pipeline itself as a modular program. It uses a small, verifiable dataset and a measurable metric, like accuracy or semantic similarity, to automatically optimize the internal prompts in few-shot examples.
So DSPy becomes the optimizer, using the failure metrics from the live system to automatically generate better internal instructions for the agent to use next time.
Exactly. This data-driven optimization allows for truly automated self-improving loops, where failure insights are back-propagated to enhance the agent's reasoning or tool calling strategy automatically, removing the human from the loop of constant, low-level instruction tuning.
We started by highlighting the need for reliability. Now we have to focus on the non-negotiable factor of security and trust. Generative AI has amplified existing risks and introduced fundamentally new ones, creating an evolving threat landscape.
It really has. Generative AI has lowered the bar for sophisticated fraud. We're seeing AI-powered phishing and social engineering at scale, such as deepfakes for voice cloning, resulting in significant financial losses.
Right.
The source material details instances like a municipality falling victim to an AI-powered voice cloning scam that successfully stole between $10,000 and $100,000 just by imitating executive voices and authorizing fraudulent transfers.
And the high-profile incidents of direct model manipulation, like the Chevrolet chatbot, are stark reminders of how accessible prompt injection attacks are to anyone with a keyboard.
The Chevrolet incident, where an attacker manipulated the chatbot into offering a $76,000 truck for $1, is a textbook example of prompt injection. This occurs when an attacker embeds malicious, hidden instructions within an input, tricking the model into overriding its safety directives or even exposing sensitive internal information.
And that's a profound danger in a BFSI
It's
context.
so huge. An attacker might inject instructions to perform an unauthorized transfer or leak customer data.
So how do engineers structurally defend against these input-based attacks?
Defense requires a multi-layered approach focused on pre-model filtering and in-model reinforcement. First, robust input sanitization has to detect and neutralize harmful, malformed, or suspicious prompts before they even reach the core language model. For prompt injection prevention specifically, a powerful technique is instruction anchoring.
Which is physically reinforcing the primary benign instructions.
Yes, you reinforce the model's primary safety instructions throughout the entire prompt structure, placing them at the beginning, middle, and end. This makes the model highly resistant to external, manipulative, and hidden instructions designed to jailbreak it.
And what about when the agent uses tools?
For tools, protection must be maximized. This is achieved by implementing rigorous sandboxing. Foundation model operations, particularly tool use, must be isolated in controlled, least privilege environments. This prevents an unintended or malicious action, maybe triggered by a successful prompt injection, from escalating into a broader system failure or unauthorized data access across dependent services. The principle of least power must be enforced by the sandbox architecture.
Organizations need a systematic framework to approach these new complex risks, as traditional security models don't fully apply to probabilistic agents.
They need a targeted threat modeling approach. We look to frameworks like Maestro, which is a risk-centric framework specifically designed for threat modeling AI systems. It addresses issues unique to agents, such as agent evasion, where an agent is tricked into bypassing its own guardrails and unauthorized actions. Maestro provides a proactive, layered defense strategy tailored to the rising complexity of multi-agent threats.
Security is also deeply intertwined with integrity. In high-stakes environments, ensuring internal decisions are traceable and sound is critical.
Absolutely. Integrity demands data provenance. This is the agent's ability to track the complete lineage and history of every piece of data it uses for decision-making.
So where it came from, how it was changed.
Exactly. This includes knowing the origin of the data, how it was processed, and what transformations it underwent. Without data provenance metadata, including timestamps, source identifiers and processing steps agents risk making critical financial or regulatory decisions based on corrupted or manipulated information. Provenance is a cornerstone for meeting audit and compliance requirements.
And central to trustworthiness in autonomous systems is the role of the human. We've mentioned human in the loop, HITL, which sounds like a safety net, but the sources frame it as a structured, intentional escalation process.
That's the key shift. HITL is a structured mechanism to bring human judgment to bear on the most ambiguous, high-risk, or novel issues. Automated pipelines flag incidents that exceed predefined error thresholds, exhibit significant drift, those PSI spikes, or involve unresolved conflicts between agents. These are then routed to a human for expert review.
And the outcome of that review has to feed back into the system.
It has to. The correct action, the refined policy, that has to feed back to improve future agent behavior, whether through updated policies, retraining, or automated prompt tuning via systems like DSPy. Escalation isn't a sign of failure. It's a critical design part of responsible autonomy.
This fundamental shift in responsibility transforms the human role entirely, moving us from hands-on executor to high-level governor of the digital workforce.
That is the ultimate evolution in mature AI systems. Governors define the policy boundaries, they set the acceptable risk tolerance, they audit systemic behavior, and they oversee complex interactions between agents and other systems. Their role shifts from executing tasks to setting the strategic constraints and ensuring compliance.
And trust must be built into that relationship between the human and the system.
Trust is calibrated, not assumed. It's built through clear communication of agent capabilities, what the agent can and cannot do. It requires full transparency, meaning the agent has to provide comprehensive explanations for its actions, revealing how it arrived at a recommendation or why it declined a request.
And the clear escalation design.
And finally, the clear escalation design. When users know the agent will reliably defer at the right moment, they are far more likely to rely on the system without dangerously overtrusting its capability.
This has been an extensive deep dive, tracing the entire stack from the most granular unit of data to the highest structures of system governance. To recap our key takeaways, production-grade AI begins with absolute data discipline filtering 15 trillion tokens down using sophisticated techniques like min-hash, perplexity, and rigorous PII remediation.
It then demands an agentic architecture that treats foundational models not just as text generators, but as specialized dynamic planners capable of action via specialized tools. These systems are designed under the principle of least power and operate under a calibrated autonomy slider to manage risk.
Scale and accuracy are achieved through hybrid strategies like ARG, which we saw moving beyond simple chunking to complex relational structures like GraphRag. This entire digital workforce is orchestrated using multi-agent systems and standardization protocols like the Model Context Protocol to manage communication.
And none of this is stable without the rigorous feedback loops of MLOps. We saw the necessity of phased rollouts via shadow and canary deployments, the shift from simple monitoring to true observability via OTel and LangFuse, and the absolute necessity of using statistical tools like KL divergence and the Population Stability Index to detect non-deterministic decay and proactively guide retraining efforts.
And finally, reliability and trustworthiness are non-negotiable requirements, demanding strong defenses against prompt injection via instruction anchoring and establishing the human as the high-level governor, defining the policy boundaries and setting the overall strategic direction of the autonomous systems.
That focus on the human governor is where I want to leave you with a final thought. We've detailed how continuous improvement and learning loops, using frameworks like DSPy for automated optimization and Expel for cross-task learning, are built directly into these agents. They're becoming automatically optimizing, highly efficient digital partners.
Right.
The future of work may revolve entirely around these interactive, agent-driven interfaces purpose-built for high-velocity decision-making, where the human role is purely oversight.
So, if the agent's decision-making pathways are automatically optimized, constantly learning and self-correcting based on vast amounts of real-time data and feedback.
The question for you, the learner and the overseer, is, how long until the human governor is no longer the arbiter of wisdom and policy, but becomes the single point of failure that struggles to keep pace with the sheer efficiency and operational complexity of their own, relentlessly self-improving autonomous digital workforce? The challenge shifts from building the system to managing your own relationship with its accelerating capabilities.
A profound challenge for anyone leading in this new era. That was the deep dive. We'll see you next time.